Hey everyone, how are you doing and welcome to a new video. So, in this video, we are going to recreate some visuals from a kind of old YouTube video, actually pretty old YouTube video. Let me show you. So the video is this one from AOKI Takamasa, which is not the AOKI DJ, Steve AOKI. This is actually another AOKI, which I guess is with the Raster Norton label, and actually this video is pretty old. It's like from 2013, so almost 10 years ago. Very old video, but I got the request from one of my patrons on how to recreate those visuals, and I gave it a shot, and in this video we're going to do it together from scratch. So, as you can see, the visual is about some particle system, which I don't know if it reacts to the sound or it just does something at every certain interval, so using a kind of a metro thing. But the particle system seems to be guided by some noise. So every time there is the kicking in, the particle system seems like it gets a new noise input or something like this. So we're going to try to recreate this from scratch. The result we're going to achieve is going to be similar to what I've played on the beginning of this video. So this is what we are aiming for. And okay, so without any further ado, let's dive in. Hey everyone, like the worst thing happened. I recorded the tutorial and then I realized I was actually not recording. So I recorded actually the first part correctly, and then I stopped it recording because I wanted to check something, and then I forgot to restart. So like the last 20 minutes were not recorded, and so I just decided to do it again, everything from scratch. This really makes me die inside, but it is what it is. So no, I'm totally fresh. So let's go for it once more. First thing, this is empty patch, new patch, everything from scratch. First thing I need is the world object. So I'm just going to get my snippet here, which I encourage you to make yourself one as well, just with a world and a camera. And that's all we need, world and camera. That's the window that has been automatically created by JitWorld. There it is. So, as you can see, I got also here ADC, so this is my audio input, which is actually coming from Black Hole. So I'm routing a sound from Spotify, I'm playing the song from AOKI Takamasa, so the one from the video, and I'm sending it out to my speakers. And then in OBS I'm actually recording it as well, using the audio input capture coming from Black Hole. So just to give you an idea of my setup at the moment. So I can like listen to it and recording it on the same time, and you get best audio quality, I guess. So what we need to do is to create a simple particle system, which we're going to do with JIT noise, which is going to give us the initial position of our particles, 3 planes. Flow 32, 400 by 400 particles is like 160,000 particles. That's going to be more than enough particles for us. Going to use a load bank to just load these as startup, just bang these out. And the frame rate is pretty variable, I guess, because I'm recording. Usually it's pretty good. It's kind of lagging, but okay. Then I need the JIT gen, because we're going to do all the particle simulation stuff in JIT gen. We could do it on the GPU with the transform feedback system, but I want to keep this video short, and I mean sort of short, and also GLSL free. So we're going to do everything on the GPU, CPU with JIT gen. Gen and GGL mesh to draw the particles. So draw mode points. I'm going to give it like point mode circle depth, because this is going to render our particles as circles, but they also have a depth. So the farther they are, the smaller they are, the closer they are, the bigger they are, as it should be. And then we're going to give it a point size of like 40. It's going to be big particles. And I'm going to connect this to the JIT gen, so if now I load bang, we can see our particles here on the window. I'm actually going to make them white, so color 1, 1, 1, 1. Good, bang again. And actually, so in all the particle systems that we created so far on the CPU and actually on the GPU as well, we need to have like a feedback loop in order to store the position of the particles, their velocity from the previous frame in order to use it on the current frame. So in order to do that on the CPU with matrices, we need to we need two matrices that have the same name, and they kind of are in a, they have access to the same space in memory, so they share the same data. So if I create a matrix called position here and a matrix called position here, this matrix is going to contain the same data. So once we update this matrix with our jitter, so the calculations inside our jitter, the matrix that is coming out here is going to share the same data with the matrix here at the beginning. So in the next frame, we will start from the position where we left it on the previous frame. I don't know if it's clear enough, but I explain it actually a lot in some other videos, which I will put a link to them like somewhere on the screen. Somewhere. I don't know about this YouTube stuff, it's really confusing. Now we need a force to move our particles, and according to me, in this video, I think the guy is like using noise sampled according to the position of the particle. It's kind of the clear effect. It kind of looks always like this. So it's using the position of the particles to sample that noise, and then the noise is applied as a force to the particle themselves. In this way, we get a continuous function where the noise is never interrupted. Like the particles, it's like if they are moving through a 3D noise, and they just get the shape of this noise. Actually, they get moved using this noise as a force. So in order to create this noise, we create a JitBFG, 3 planes, 432, 400 by 400 particles. Let's give it even a third dimension because we're going to use the x, y, and z position of the particles to get the noise. I'm not sure exactly if we need this third dimension, but let's just add it. And we're going to sample those particles as this noise using the position of the particles. Oh, let's actually give it a basis. So let's give it an attribute basis, noise.simplex. Let me make the music a bit more silent for me. For you should be okay, I hope. And so let's go inside jitter, and let's create the second output here, which we are going to use as the position of the particles to sample the noise. And we're going to create a second output because we actually want to scale the position of the particles in order to have a different scale for the noise. So it's like when we created the scale attribute for the JitBFG, but this time we using the position of the particles to sample the noise. So we actually need to sample to scale the position of the particles to get a different scale for the noise. So let's create this parameter. Let's call it scale, or maybe noise scale. It's better. Let's create a default value of 1. So here noise scale. Cool. And this is going to be the position of the particles scale that goes into the noise. The noise goes back into the jitter, and actually we should continuously trigger this position matrix in order to get the particles moving. And as you saw, they just go super fast away because the force of the noise is like big numbers. So we actually want to multiply that by, let's say, a new parameter which we'll call force amount. Doesn't exist yet, so let's create a new param force amount, and let's set it to 0.002 or something. This should be maybe okay. Okay, so as you can see, the particles are moving now according to this noise, which is good. It's good. We can create our scale, noise scale parameter to set the scale of the noise. I'll show you how this works. So if we want to get like a scale of 0.2, let's see, the noise is now smaller. If we get a bigger scale, the noise is very high frequency variations between one particle and the others. And as you can see, it's actually not really symmetric. The noise is going in one direction, and that's because we need to set the at basis sign set to 1 for the JitBFG object. This is going to give us a more symmetric noise. Exactly. Let's load bang that. Let's load bang this dude, and yeah, this looks good. Scale it back to 1. Okay, so that's good. But what we want to have, if we take a look at this video, is like the noise is not continuously applied. At least it doesn't look like this to me. What I want to do is that the noise force gets smaller and smaller every frame. So like we get a kick, a bang, we trigger this noise force. It gets applied to the particles, but then like slows down and stops in like a couple of moments. So in order to do that, we first want to, let's make a bit more space here. Okay, we first want to not send continuously this matrix to the JIT gen, so the noise matrix to the JIT gen. We don't want to send it continuously. We want to create a new JIT matrix with true set to 0, so it will not allow matrices to pass through, only when it receives a bang. And then we want to create again another loop of matrices to make this force get smaller and smaller at every frame. So we're going to call this matrix velocity. It's actually, let's cut out the third dimensions, the third dimension, so let's make 3 plane, 432 400 by 400. And we need another matrix called velocity. This we can just give it just a name, it will just get the same characteristic as the other matrix called velocity. And let's create a new output here. So inside JITGen, which I'm going to call output 3. Let me make sure I'm recording, because this is going to be really bad if I'm not recording, but apparently I am. So this is going to be simply the noise coming in, but before we send it out, we multiply it by some feedback. Another parameter which doesn't exist. So we create a new parameter, call it feedback 0.7 or something. Good. This looks pretty cool actually, but it's not what we want. So this goes out to the JIT matrix velocity, and actually we should also continuously trigger this velocity matrix as well. So I first send a bang to the matrix velocity, then send a bang to the position in order to get the particles moving. So as you can see, if I just start the system, there is an old matrix being applied, but every time I click on this bang attached to the true, you can see that the matrix start to move, and they will stop moving after a certain amount of time decided by the feedback. So let's create a new parameter. Let's call it feedback, and let's set it to, I don't know, 0.8, 0.9, 99. And then you can see that they start moving and they don't stop until the feedback is exhausted. So to give it like a nice ease effect. And let's actually trigger this matrix using the kick from the sound. So let's put it somewhere here where you can see it. I'm going to get this is our input, so the music. Since I just want to get the kick, I'm just going to create a new object, cross filter, which filters around like 250. This should give us the lowest end of the spectrum, and I'm then going to use the average object with 2000 samples or something, RMS, and this should give us like some sort of envelope following of the sound, of the buses of the sound. It looks good. Let's maybe multiply that by some bigger value, just to have a clearer result. Oh, that's kind of a lot of DC offsets. So I'm going to create another cross, and this time I'm just going to get the higher frequencies. So yeah, we center it back around the center of the scope, which is good. We cut out all the DC offset. Nice. Let's now create a snapshot, and this is going to give us the max values. Oops, sorry, scope. Didn't meant to be rude. So let's create a receiver for our bang, because we're going to trigger the snapshot once per frame. Numbers we're getting from the snapshot, those. Oh, the music just stopped because the song is finished. Let's see if it starts again. Okay. So, okay, so let's say that we want to trigger a bang every time the audio goes above, so I cannot make greater than sign anymore on this keyboard. I don't know what's wrong. So let's say every time that this is greater than 0.5, or shall we say 0.4. It seems like it's kind of getting the kick and every loud sound, but it's okay. Good. Let's use a change object so we only get the values when they change. And actually, let's get rid of this. This could actually be useful. Yeah, this. Let's get rid of the scope, I guess, to save a bit of CPU cycles. And then let's say select one. And let's send this out as our audio bang. So every time this is true, it will send us an audio bang. Use the change to not get a continuous stream of ones and zero. I hope you can see that, not covered by my camera. It looks okay. Good. So let's receive this audio bang here, in which we trigger the JIT matrix output. Where did I connect it? Okay. Okay, so this looks good. Let's see. Okay, this looks good. We can also change the, I think we have another parameter called force amount. So let's create a new message. Force amount. And let's set it to something higher. Oh, this is very high. Too much, too much. Something like this. No, still too much, especially with such a big feedback. If we reduce the feedback, then it's better. Okay, noise scale, let's reduce it to like 0.2. There is a lot about, it is a lot about playing with the parameters for this patch. And if we want to play with parameters, then we need also a preset to store those parameters. So I'm going to store this preset here. And cool, so as you can see, it's kind of reacting to the kick. Every time there's a kick, it sends a new matrix, but it's a bit boring because it's only following the same noise, so it's just expanding on the same noise, which is not what we want. What we want is actually to send an offset every time we receive a kick. So it's going to sample the noise at a different place every time. So let's create a new parameter in JIT-gen, an offset with 3 parameters. And then after we scale the position of the particles, we are going to sum it to an offset to sample the noise at a different place every time we receive a kick. So let's create this noise, this offset, which we are going to use a random number to get it, like, I don't know, random 100,000 or something. And let's use a UZI3 object. So every time we receive this audio bang, we first trigger this UZI, which sends out 3 bangs. According to this random, we list.group these 3 numbers into a list. Okay, and then can you see that? Oh, so you have to get used to this camera stuff. And then we say just prepend offset, and this should work nicely. Let's connect this to JIT-gen, and let's start from scratch. Okay, a bit more force. Oh, actually, I think I saved those values, so okay. A bit more feedback. Okay, so this looks good. They are going to go expanding indefinitely. If we want to get it a bit more reactive, we can make this 0.4 smaller. Yeah, this looks better. And okay, we could have also the scale changing automatically every time we receive an audio bang. So in order to do that, let's maybe add another bang here. Let's create a random object which gives us random numbers between 0 and actually 100, so 100 to 1. And let's divide this by 200, so it gives us number between 0 and 0.5. We connect it to the noise scale, and so we get a different noise scale at every time we receive a bang, which could be interesting. Could have a bit more force, could have a bit less feedback, a bit more force, less feedback. It's a lot about playing with the parameters, as we said, yeah. But I guess this goes pretty close to the same technique used in the video. Of course, there is also a lot of camera movements involved here. which we can definitely just get ourselves by creating a different random position for the camera. Okay, maybe a bit more feedback in order to give it this kind of ease effect. Yeah, let's maybe add an offset of 0.1 to the noise scale, so it's going to be minimum 0.1. Yeah, okay. This looks reasonable. We could make that the particles, since they are going to expand indefinitely otherwise, maybe I would like to have that they actually stay close. They have a kind of attracted back to the center of the world. Maybe we can use the position of the noise to create a vector that goes from the noise to the particle position. Actually, from the particle position to the noise, we normalize that. So it's as a magnitude of 1. We multiply it by something small, and then we use it as a force for the particles as well. So this is going to bring them toward the center. Show you how this looks. Toward the noise, actually. So they're not going to expand indefinitely. That's the point. Let me apply again our values. Yep. Can I have this force in bigger? Could be that in the video something like this is applied as well. But it's kind of my personal contribution to the visuals. Okay. Maybe we don't want a random scale, we just want to have always the same scale, around 0.3. Yeah, it's a lot about playing around with the parameters. One thing I want to do to make it cooler is to create a GGL pass with an FX name of Bloom HQ. Don't use the normal Bloom, use the Bloom HQ because it looks so much better. Don't use just the Bloom effect, use the Bloom HQ. Good, so what we want to do is to change the threshold of the bloom, and by default it's 1.5, so once we go below 1 it's going to apply the bloom, but it's going to apply to everything, which is not really cool. So what we want to do is to go into GGL mesh, set the blend enable to 1, the blend to add, and also depth enable to 0, so all the stuff for the blending. You cannot see that, right? So let me make these on multiple levels. So blend enable 1, blend add, and depth enable 0. So what happens that now the bloom will only be applied where the particles overimpose with each other. So it's going to be a much nicer effect. Cool. This looks extremely good. Let's maybe change the background of the world to black instead of having this grayish color. And if we save these into the preset, it's going to be saved as well with the preset. Let's maybe make this force that brings the particle back to the origin even bigger. Yeah, something like that. So then we can afford to have like a bigger... It's not bringing them back to the origin, it's actually bringing them back to the position of the noise for some reason, but I think this is interesting. Okay, good. Let's look at this 1 second with kind of the music. High volume. And I would say it looks pretty good. It's maybe not exactly the same as in the video, but this is how close we can get with this amount of time on one of my tutorials at least. So yeah, I guess this is it. Thank you very much for following, people. I hope you found this useful, and actually if you liked the video, it would be great if you put a like to the video, subscribe to the channel, and then check out my Patreon to download this patch and a lot of other ones, and also get in touch with me through Discord. Cool. It was actually good that I had to remake it once again from scratch, because then I got a lot of stuff better explained, I think. Okay, that's just a note for myself. Good, people. I hope you had fun, and I will see you in the next video. Ciao, ciao.